Now we're going to talk a little bit about displaying, visualizing, primarily performance data, but really try to get you thinking a little bit about visualizing any kind of data, results for users, or mainly in this case, graphs for reports or for papers or these kind of things. But of course, because of course, you know, when we're producing results, we're going to have to display them in some form or another. And we talked previously about using profiling to let you optimize a code. Once you've optimized the code, you want to be able to work out how much you've optimized it by, and then potentially, if you're writing a paper about that or a report for somebody, you'd want to be able to document and display how much you'd optimize it. And a lot of the issues we see with inexperienced researchers publishing papers or writing reports is that it's very easy to draw a simple graph of my code went faster, look at this line which shows it goes faster, but it doesn't always necessarily convey the data correctly or in the most sensible way. So if you can have a little think about how you're displaying your data before you go ahead and publish it or report it, that will help going down the line. So it's always, data you can always show data in. So the two things we want to know to understand is there are always more than one way to display data for people, and it's also necessary to consider errors in your data and consider displaying some assessment of those errors for people who are reading your reports or your papers or viewing your visualizations. And in this context, errors may be performance variations. So if you run a code 10 times and you time it, it's unlikely that all 10 timings will produce exactly the same result. So you'll have some variation there, and it's useful to be able to understand how much variation and what kind of variation, because if your code runs 5 times faster and those results are plus or minus 5%, then people say fine, you've done a good job. If your code runs 5 times faster but the results vary very widely, then people may question the kind of approach you're taking. And of course, there are multiple ways to display data: tables, graphs, pictures, animations, videos. Really, what you choose depends on the kind of data you're trying to display. But you need to think about that a little bit. And I have an example here from not work that I've done myself, but work done by others on visualizing tumor data inside a patient collected from some kind of medical scanner. Here the data will be collected and then it will be processed and that turned into a visualization. And in this context, this data was turned into a visualization for surgeons to understand whether they needed to operate, and then if they're operating, how much material to remove from a patient. And this is great. You can see what's going on with this visualization. Looks fine, but of course there is only one picture shown here. There is no uncertainty, there is no quantification of any kind of errors or variation in the results here, but in reality this data is collected from a bunch of different scans from machines which may have some kind of error associated with them, and then a visualization algorithm has been used to reconstruct the data, which again may have some kind of error associated with it. So in this context, rather than just showing a single shape, if the person who produced this was able to show a shape with some kind of error bars on it, or different surfaces showing the minimum maximum size they expected this tumour to be based on their understanding of the errors in their models and their reconstructions, then it would be much more useful for someone to use, because they would be able to understand exactly how much tissue they should really take out or where the variation may be. And it's that kind of, this is quite a serious example, but in everything we do in science and data analytics is always going to have some kind of uncertainty about it, and being able to display that to the users, not just display a single result, hiding all the uncertainty and all the potential errors, you'll end up with much better understanding by users and much better appreciation of what's going on. So to bring it back to something more relevant to work you may be doing in this course or in other courses, here I've got an example. I've taken a code, and in this case it's not optimizing it, it's parallelizing it. So I've taken it, I've run it on one processor, and then run it all the way up to 16 processors, and I've collected some data. And that's a perfectly fine way of displaying the data. Of course, a lot of people would choose to stick it in a graph. So here I've used Excel, and I've just plotted that, and it's showing the same data. The data hasn't changed, just a different way of presenting it. Of course, this is not a very good graph because I don't have labels for my axes, I don't have units on there, but also at a sort of higher level, it's quite hard for me to hit with this graph, understand actually, is this good performance or not? So I can see the runtime at one processor and the runtime at 16 processors, but if this was parallelizing perfectly, is the actual result I got close to what I would expect if it was perfectly parallel or not? So I can augment my graph and add some extra detail on, like, here's a trend line, which if the code had been parallelized perfectly, then we could see, then it would take this bottom curve and the actual data to the top curve, and suddenly now I've added a bit of detail to my graph, a bit of additional input, and it's easier now to understand the performance I'm getting. And you can see now, actually, no, I haven't done a very good job of my parallelization. It's much slower than the ideal performance would suggest. So we're not doing great. But you'll find people also do other ways of presenting this data. So we can see that just plotting the speed up, the ideal speed up on a linear graph like this doesn't have necessarily a straightforward relationship between the x and y axis, but we could, and you quite often see this for a lot of scientific graphs, plot it using a log linear plot or a log plot here. So now my ideal speed up has become linear. I can see my linear speed up down here, and I can also see my speed up of my actual result here, and I can see there's a big gap between them. So again, the same data being used here, it's not changed, but it may be easier for some people to understand that this linear line here is the ideal speed up in a log plot, and this is my actual line. I can also take my data and calculate actual speed up from it, so how much faster I'm going. And again, here I've done something not very nice. I've swapped over my colours, so it's a little bit annoying, but we can see that's also another perfectly acceptable way of displaying my results here. Same data again. Here I've just processed it a bit and visualized it, and of course I can do that on a log plot as well. And so, whether you choose to display your data just like this or all the way down like this very much depends on what data you're trying to present and what you expect your audience to be. At some level, I find this single table a little bit difficult to work out exactly if I'm getting good performance here, but then of course I could add another column of data down here to show what the ideal performance would be, and then the gap between my actual performance and the ideal performance would be much more visible, and that would be a fine thing to do. But also likewise, these graphs show me the data, and so do these graphs. So I'm reasonably happy with those. But of course, there are things to watch out for in these kinds of process data metrics. So before we discussed, you could take your runtime and turn it into speed up, and that may demonstrate usefully how good your code is here. So this is my graph I showed before, but it's not runtime, it's speed up. But of course, then that doesn't necessarily always tell you exactly what you expect it to tell you. So here now, I've got the blue line here, this bottom line here, is my original data. Speed up for my original data. I've not changed it anymore. Now this top line is a new version of a code which I've created, and I've done my collected my results, my timing results from that new version of the code, and I've plotted the two of them together, and this is now speed up rather than runtime. And so I've got two versions of my code. They're both parallelized. I want to see which is my best code here. And so naively looking at this graph, again I should have labeled the axes here, but looking at this graph, this new code, the optimized code, is much better than my old code. You know, it's not nowhere near perfect. At 16 processors, it's only 3 times faster than at 1 processor, so that would be nowhere near linear speed up. Nowhere near one of these lines here where you can see at 16 processors it's 16 times faster, but it's still, you know, twice as fast as my original code. So I could look at this, and if someone presented this to you, you could naively assume that the optimized code has done a really good job, and you know, you'd like to use the optimized code rather than the original code. But remember that this is displaying speed up, which is a metric derived from the time. So it's something I've calculated from the runtime, and it's not showing me actual time to solution. So it's not necessarily telling me all I want to know. So again, I can plot on an ideal speed up or an ideal speed up on log part. But actually, if I took my runtime data, the time to solution here, and plotted that instead of speed up, we can see that actually my original code, even though it doesn't speed up as well as my optimized code, my original code is always faster than this top line, this optimized code up here. So I can see that the work I've done hasn't really improved the performance of my application. It's just made it get better as you parallelize more. But even at the high level of parallelization at 16 processors here, I'm still not beating my original code. So actually, even though my speed up graph here shows that the optimized code speeds up better than the original code, the actual time to solution graph shows that my original code is still preferable. You know, most of the time, and in fact all the time, what you really care about is time to solution, how long it takes to solve a simulation or undertake some data analysis. So you can see that it was quite straightforward for me to actually display correct results here, looking at speed up, but the correct results didn't really tell the story that I was trying to tell here. It looks like my optimized code is better, and indeed it has better speed up, but it doesn't have better time to solution. And so you've got to be careful when displaying things like this about what metrics you choose to display, to use in your reports and in your papers and these kind of things, so that you are showing a true reflection of how a user would use the code and the performance a user would see. And for instance, if I'd have just taken my table and instead of showing speed up, I've got my original code and my new code, and just do runtime, it's quite obvious from that table what's going on here. And so there's a really a quite nice set of articles or blog posts and papers actually on sort of issues with presenting performance in high performance computing and computer optimization, based on David Bailey's original article, 12 Ways to Fool the Masses When Giving Performance Results on Parallel Computers, and extended by George Hager on his blog about fooling the masses. And so there's lots of different ways to present your results, so it looks like you've done a good job even if you haven't, which is worth trying to guard against and trying to not fall into these traps themselves. There are things like this exact example, report speed up, not absolute performance, which is what we've just discussed. To slow your code down to make the serial performance terrible, so your parallel performance look better. Use a log graph, because a log graph, the speed up looks better, closer to ideal on a log graph than it does on a normal graph. So go and have a look at George's blog post and have a look at the original article. It's worth reading up at, and in the end, think about the performance of a data, either performance data or whatever data it is you're trying to display. Try and display it in such a way that it tells the correct story and not just a story you would like it to tell, because it's always tempting to try and promote the work you've done in the most positive way, but it's best to promote it in the most pragmatic way, and always ensure that you think about variation and display that as well, because actually when we're doing performance benchmarking, what we want to do is run a code a number of times, 5 times, 10 times, collect all the timings and then report consistently on those timings. So you might want to report the fastest run and then tell people what the difference between the fastest and the slowest one was. Or you might want to take those 10 timings and report an average, or you might want to take the slowest. Any of those options is fine. You just need to be consistent when you're reporting your numbers, that you always report for a given report or paper, you're always using the same metrics. And when you write a performance report or you write a paper, you want to also give people enough background information about what you've done so that they could reproduce it. So you want to tell people what kind of hardware you ran your tests on, what software you were using, so operating system, compiler, that kind of stuff. You want to put all these in there somewhere when you're talking about your results. You want to document first how you did them, and then tell people how many times you repeated your results, what results you're displaying, is it the maximum, minimum, average. And then when you display these results, you may want to add in there some visual representation of the variability of results, so error bars showing the standard deviation of a result or something like that. So try and bear these in mind when doing performance results and when looking at when writing up scientific data.